Hi, welcome back. This is now test 3 review for Math 1620. I just want to go through and give you the kind of question pool from WebAssign and do some example problems from every section and kind of give you a heads up and remind you of what you're up against. Okay, so 8.1, any question 1 to 12. Basically, this was just a review of all of your techniques from Calc 1 with regards to integration. Let's look at a couple problems. Basically, can you do U-subs, all the little tricks like separating fractions and finding ways to dispel with particular integrals. In this case, we have kind of a simple integral, an integral that I hope you could do without a U-sub. Ultimately, some of these integrals you want to be able to do in your head. And here, if you did a U-sub, you would get 9 dx, and then you'd get a 1 over 9. So dx is 1 over 9 du, right? So you would have a constant of 1 over 9. And then the antiderivative of cosine 9x is sine of 9x, times the 1 over 9. The idea is kind of the reverse of the chain rule. So if you're taking the derivative of sine of 9x, it would be cosine of 9x times 9. When you do the integral, instead of multiplying by 9, you're going to divide by the 9. Okay, so, worst comes to worst, just do your U-sub. Anyways, let's go ahead and evaluate this thing. So first plugging in pi over 18 into the antiderivative. 9 times pi over 18 is the same as pi over 2, and then minus 1/9 the sine of 0. Sine of pi over 2 is 1, and then sine of 0 is 0, so you're just going to get 1/9 for your answer. So doing some U-subs, let's try number 9, 19, tan x ln of cosine x dx. Here, the U-sub is for ln cosine x. If you tried something else, you wouldn't be able to reduce the number of symbols once you simplify. So U must be the ln of cosine of x. The derivative of the differential is going to be 1 over cosine x times negative sine x dx. And if you rewrote that, that's the same thing as negative tan x dx. Okay, and then solving for dx, I'd get negative du over tan x. And substituting that into my integral, I can factor out the 19. I get tan x times u times dx, which is now negative du over tan x. Simplify, remove the tans, bring the negative out in front. So you get negative 19 integral u du, and then do a power rule. So negative 19 u squared over 2 plus c. Back sub, and you're done. Right? So negative 19 halves times ln of cosine of x squared plus your integration constant. Okay? Okay, so that was, make sure you can handle those kinds of problems. 8.2, we get into our first kind of new method, which was by parts. So remember, liate to tell you what is u. Let's try number 6. Here we have 9 arc tan of x. So this one doesn't really look like it fits the bill of by parts. But if you let u equal the arc tan of x, and then I'll just let dv equal dx, you can do the by parts and it'll work out. So the derivative of u will be 1 over 1 plus x squared dx, and then integrating just dx is going to be x, and then you could rewrite this. Let me factor out that 9 out of everything, I guess. You would get x arc tan x minus the integral of x times 1 over 1 plus x squared. So in this case, you're going to need a u-sub on the second term here. So u would just be the denominator, So du is 2x dx, and then dx is du over 2x. Okay, so this integral will become, let me distribute the 9. 9x arc tan x minus 9, this integral of x over u times dx, which is now du over 2x. That'll become 9x arc tan x minus, you can factor out a 2, get 9 halves, the x's cancel, and you just have the integral of du over u. That'll be 9x arc tan x minus 9 halves ln absolute value of u. Let's see, and then finally back sub. So you get 9x arc tan x minus 9 halves ln absolute value of 1 plus x squared. You don't need the absolute value this time, but it doesn't hurt to put it in there. Okay, so that's number 6. Let's look at number 9. Number 9 is one of these ones where you kind of have to integrate by parts until you get back to where you started, and then assign a variable and solve for the integral. Okay, so on top of everything, we have to evaluate this guy. So let's take a look. So from Liate, we have trig before exponential, so I'm going to let my u be sine x, and my dv be e to the x dx. du is going to be then cosine x dx, and then v will just be e to the x. Okay. So this is going to be e to the x sine x minus the integral of e to the x cosine x dx. And then I got to do my parts again on this guy. So again, Liate says trig before exponential. So du will be negative sine x dx, and then v will be e to the x. Okay, so this one's this, and then minus that integral. So we're getting e to the x sine x minus e to the x cosine x minus negative, so that become a plus integral of e to the x sine x dx. And here is the issue then. You can see this integral here is also sitting right here. Okay, so we want to give that a variable name and solve for that. So I have I equals e to the x sine x. Let me distribute this negative through. Minus e to the x cosine x minus I. Add I to both sides, you get 2i equals e to the x sine x minus e to the x cosine x. I got to remind myself to evaluate eventually. Divide by 2, and you just get e to the x sine x minus e to the x cosine x all over 2. And I need to evaluate this from 0 to 7. Okay. All right, so plugging in 7, I'm not going to get anything pretty, but I have e to the 7 times sine of 7 minus e to the 7 cosine of 7 all over 2. And then minus, if I plug 0 in the sine, that part's going to be 0. And then 0 into the cosine part, I get e to the 0 is 1, cosine of 0 is 1, so it's going to be negative 1/2. So minus negative 1/2 is plus 1/2, and then that would be my answer there. Okay. If you have something strange like that, you could leave it in terms of sines and exponentials. You don't need an approximation on my test. Anyways, 8.3, we're looking at problems 1 to 11. These are trigonometric integrals, so there's some basic formulas you need to have memorized. Any of the Pythagorean identities like sine squared plus cosine squared is 1, or 1 plus tan squared is secant squared, those things. You also need like the sine squared theta is 1 minus cosine 2 theta over 2. The cosine squared of theta is 1 plus cosine 2 theta over 2. Those things, right? So sine of 2 theta is 2 sine theta, cosine theta. Okay. Let's look at number 2. It was the integral of sine to the 4th of 3 theta d theta. We need to use this formula right off the bat. It's sometimes called a power reduction formula because it'll get rid of those exponents. So sine to the fourth is really sine squared squared. So sine squared squared d theta. So I'm going to replace this junk inside with the 1 minus cosine of the double of the angle. So I'm going to get 1 minus cosine of 6 theta. So you have to multiply the 3 theta by 2, all over 2 squared d theta. Then I got to kind of FOIL out the numerator. The bottom would be 4. So get 1 minus 2 cosine 6 theta plus cosine squared 6 theta d theta. I'm going to separate this sort of fraction into 3 parts. So 1/4 minus cosine 6 theta all over 2 plus, I guess, 1/4 cosine squared 6 theta d theta. Again, I'm going to do a power reduction formula on this one. So this time I need to replace it using this guy. So I'll have, as soon as my pen works, I have the integral of 1/4 minus cosine of 6 theta all over 2 plus 1/4 times 1 plus cosine of 12 theta all over 2 d theta. I'm going to kind of combine like terms before I get carried away here and start integrating. So I have 1/4 minus cosine of 6 theta all over 2. If I separate this 1 plus cosine 12 theta over 2 in the 2 parts, I'll have, and then multiply by the 1/4, I'll have 1/8 plus 1/8 cosine of 12 theta d theta. And then I can combine the 1/8 and the 1/4. So the 1/4 is the same as 2/8. In other words, I have the integral of 3/8 minus cosine of 6 theta over 2 plus 1/8 cosine of 12 theta. So now I'm going to go ahead and integrate. Okay, so I get 3/8 theta minus, again, if you take the integral of cosine 6 theta, basically you're just going to be dividing by 6. Okay, so this would be sine of 6 theta over 12. And then the integral of cosine 12 theta, you're going to end up dividing by 12, right? So it'd be sine of 12 theta all over 8 times 12, which I would think is 96. Okay, and that'd be your answer. Let's look at one of these ones where you have kind of a product of trig functions. So those were kind of typical in this section. You have secant squared of x over 40 times tan of x over 40. So in some of these you have to kind of mess around with them and use the Pythagorean identities. This one is kind of nice though. You could just do a u sub on tan x over 40. And then du will be secant squared of x over 40 times 1 over 40. And you see you get a nice cancellation happening. So dx can be replaced with 40 all over secant squared of x over 40 du. So what do we have then? The integral becomes the integral of secant squared of x over 40 times u times dx, which is now 40 all over secant squared of x over 40 du. So nice little cancellation on those guys. Factor out the 40, so the integral of u du, power rule it, and I end up with 20 u squared plus c, back subbing 20 of tan of x over 40 squared plus c. Okay, so hopefully those are kind of smooth sailing. Moving on into the trigonometric substitutions, then we have 8.4. Any problems like 1 to 13. Based on the form of the integral, the square root part, you know what your sub has to be, right? So if you have square root of a squared minus u squared, that tells you you need to do an a sine, u equals a sine theta. If you have square root of a squared plus u squared, that tells you u has to be a tan theta. And if you have the square root of u squared minus a squared, that's u equals a secant theta. Okay, and these are the ones where you have to do the triangle and all that jazz. So let's look at number 2. We have the integral of the square root of 64 minus x squared all over x dx. And from the form, I can tell it's a sine sub. So our x in this case will be 8 sine theta. And I like to get all my information first, and then I'll go ahead and start subbing. Dx from here will just be 8 cosine theta d theta. Solving for theta, theta equals sine inverse of x over 8. My triangle, here's theta, it's a right triangle. Sine is opposite over hypotenuse, and then the third side would just be 64 minus x squared. Okay, so I got all my information, and now I can work on my integral. So doing subs, I have the square root of 64 minus 64 sine squared theta all over x, which is 8 sine theta. And then don't forget dx is 8 cosine theta d theta. Okay, this thing up top you can rewrite as the square root of 64 times 1 minus sine squared theta. Then you can replace 1 minus sine squared, of course, with cosine squared. So you get square root of 64 cosine squared theta. And then we could rewrite that by taking the square root. So you get 8 cosine theta all over 8 sine theta times 8 cosine theta d theta. And what these usually do, what usually happens now is you get a trig integral, right? So let's factor out an 8. These 8's cancel, and you can factor out an 8. Then you'd have cosine squared over theta all over sine theta d theta. If it's not clear what to do here, you got to use Pythagorean identity on that cosine squared. All right, so cosine squared is the same as 1 minus sine squared theta all over sine theta. And then you could go ahead and butterfly that thing. So you get 8 integral 1 over sine theta is cosecant theta, and then sine squared over sine is just sine theta. Both of those are well-known integrals. If I put cosecant, the integral cosecant on a test, I'd help you out with a hint formula. But cosecant is ln of the absolute value of cosecant theta minus cotan theta. And then the integral of sine theta, of course, is negative cosine theta, so it's become plus cosine theta, and then plus c. And now I want to go to my triangle and replace all the cosecants and cotans and cosines with terms of x, right? So cosecant, remember, 1 over sine, so that's going to be hypotenuse over opposite from the triangle. Okay. Cotan is going to be then adjacent over opposite. So you have to know all those kind of quotient identities for triangles and trig functions. And then plus 8 cosine of theta is going to be adjacent over hypotenuse. So square root of 64 minus x squared all over 8. Let's see, and then you could simplify a little bit if you want to. 8 ln absolute value 8 over x minus the square root of 64 minus x squared over x plus square root 64 minus x squared plus c. Okay. Let's look at another one. This is number 3. The integral of the square root of x squared minus 16 all over x dx. Okay, so from the form of this guy, it's a secant sub. So x is going to be 4 secant theta. Let's get all the information. So dx is going to be 4 secant theta tan theta d theta. Theta will be secant inverse of x over 4, and then get your triangle. And so triangle here. Secant is 1 over cosine, so this would be like adjacent over hypotenuse, and this third side would be, hypotenuse over adjacent, sorry. So hypotenuse over adjacent, the third side would be square root x squared minus 16 from the Pythagorean theorem. Box all that junk off. Okay, so I'll have the integral of the square root of 16 secant squared theta minus 16 all over x, which is 4 secant theta, times dx, which is 4 secant theta tan theta d theta. So we can rewrite this, right? So this would be 16 times secant squared theta minus 1. Secant squared theta minus 1 is just tan squared. So this would be the square root of 16 tan squared. Then taking the square root of that, I'll have 4 tan theta all over 4 secant theta times 4 secant theta tan theta d theta. And of course our 4 secant thetas cancel, factor out 4, you get the integral of tan squared theta. From our trigonometric section on trig integrals, the way you work with tan squared is to just replace it with secant squared minus 1. So secant squared minus theta minus 1 theta. These are from your Pythagorean identity. So this would be 4. The integral of secant squared is just tan theta, and then minus 4 theta plus c. Go to your triangle. Tan is going to be opposite over adjacent. And then theta, unfortunately, you have to leave that as kind of secant inverse of x over 4. Let's see, I could clean it up a little bit. Okay, that's, you know, those, I think those are like the hardest kind of integrals that we do. But yeah, probably see 2 of those on the test, 1 or 2 of those. Anyways, 8.5 now, moving on, partial fraction decomposition. Remember there are 4 types, the linear repeated, irreducible, and irreducible repeated. Let's look at number 2. So I have x squared plus 60x plus 60 all over the x cubed minus 4x dx, right? I need to do a partial fraction decomposition on this guy. So x squared plus 60x plus 60, I'm going to factor that denominator. So this is really the same as x times x squared minus 4. And that's the same as x times x minus 2 times x plus 2. So it's just a bunch of linear factors. It shouldn't be too hard to deal with. Okay, so I have a over x plus b all over x minus 2 plus c all over x plus 2. Your first step is to multiply through to get rid of all the denominators. So you're going to end up with x squared plus 60x plus 60 equals a times x minus 2 times x plus 2 plus b, the x minus 2's would cancel, so you have x times x plus 2 plus c, and the x minus 2 and the x would be left. So x times x minus 2. I'll use that, I forget which method, but it's kind of like a substitution method. You just plug in to get rid of the x's and some of the variables, some of the constants, a, b, or c. So if you let x equal 0, and plug x in everywhere, you get 0 plus 60 times 0, which is 0 plus 60 equals, and if you plug in 0 on the right, a times negative 2 times positive 2 would be negative 4a, and then b times 0 times 2 is 0, plus c times 0 times negative 2 is 0. So all that junk is just 0, and you have a then equals negative 15. Plug in x equals 2, so I'd have 40 plus 120 plus, or sorry, 4 plus 120 plus 60, so 184. And then on the right side, the a times 0 times 4 would be 0, plus b times 2 times 4 would be 8b, and then c times 2 times 0 would be 0. So you get 184 equals 8b, so b, if you do the division on your calculator, is 23. And then let x equal negative 2. So here on the left, you get 4 minus 120 plus 60 is negative 56. On the right, the first two terms now will be 0, and the third term, c times negative 2 times negative 4, is 8c. Divide by 8 on both sides, you get negative 7. Okay. After you do that, then we want to rewrite our integral. So I got negative 15 over x plus 23 all over x minus 2 minus 7 all over x plus 2 dx. And then these are just some natural logs, right? So negative 15 ln absolute value of x. You can do a u sub. It's not going to be necessary, though. 23 ln absolute value x minus 2 minus 7 ln absolute value x plus 2 plus c. Okay. All right. Let's do one with an irreducible quadratic. This is number 5 in my math lab, or WebAssign. 9 minus x squared all over 7x cubed plus x dx. Okay, so that denominator this time, if you factor on an x, you get x times 7x squared plus 1. So you get a linear factor, the x, times an irreducible quadratic. Okay, so let's set up our partial fraction decomposition. So there's from the linear, and then from the irreducible quadratic in the numerator, you have to put bx plus c. Okay, so 7x squared plus 1 in the denominator. Multiply through to get rid of the denominators by x times 7x squared plus 1. On the right, you'll have a times 7x squared plus 1 left, plus bx plus c, and just the x will be left there. We'll have 9 minus x squared equals 7ax squared plus a plus bx squared plus cx. I want to equate coefficients this time. On the left, you could rewrite it if you wish as negative x squared plus 0x plus 9. And then on the right, you'd have 7 a plus bx squared plus cx plus a. So you have 7a plus b equaling negative 1, then c equals 0, and a equals 9. Plugging in 9 for a, you get 63 plus b equals negative 1, so b is apparently negative 64. Okay, then I can go back and rewrite my integral using this information. My integral will become 9 over x minus 64x plus 0 all over 7x squared plus 1. Okay, the first integral is just a natural log, so it would be 9 ln absolute value of x. The second integral, you're going to have to do a u sub on. So u for 7x squared plus 1, the differential du 14 x dx. So dx will equal du all over 14x. So my second integral, you could factor out a 64 and eventually factor out a 14. Then you have the integral of x all over u times du all over x. Okay. The x's cancel. You get 9 ln absolute value of x minus 32 over 7 integral of du over u, which is a natural log. So 9 ln absolute value of x minus 32 sevenths ln absolute value of u. Let's back sub though. 7x squared plus 1 plus c. Okay, so those problems are long too, but it's just a matter of computation. There's not a lot of creative thinking involved here. Anyways, let's move on then. The next section is 5.6. It was all about limits, and in particular L'Hopital's rule. So there's kind of the standard limit problems where maybe you're having to do L'Hopital's once or twice. Here we have something in one of those forms. So you do L'Hopital's when you have 0 over 0 or some version of infinity over infinity. We have an infinity over infinity form here. So x cubed will go to infinity as x goes to infinity. And then 5e to the x over 3 will also go to infinity. Okay. So I can do L'Hopital's. You can take the derivative of the top, which will be 3x squared. The derivative of the bottom is going to end up being 5/3 e to the x over 3. Investigate it again. This time 3x squared will be a parabola. It'll go to infinity as x goes to infinity. The bottom will also, again, go to infinity. So you do L'Hopital's again. So I get 6x all over 5/9 e to the x over 3. Again, 6x is now just a straight line, but it'll still go to infinity as x goes to infinity. And same for the exponential. So you do L'Hopital's again. This time you get 6 all over 5/27 e to the x over 3. Now you have an L over infinity form, which is always just 0. Okay, so you have the standard versions. Then you have all these kind of new indeterminate forms, like 0 times infinity, infinity to the 0, infinity minus infinity. And I usually put one of each on the test, so let's take a look at one of each. So first I have x going to infinity of x sine of 6 over x. If you investigate here, plugging in infinity to x, you'll have infinity. And then sine of 6 over x as x goes to infinity is going to be sine of 0, which is 0. Okay? So the trick for these is to rewrite them as fractions. And I have to be a little clever here. X is the same as 1 over 1 over x. So I could rewrite it like that. Sorry, not 6, but x. Okay, now I can do L'Hopital's because it's a 0 over 0 form. So the derivative of sine of 6 over x is cosine of 6 over x times negative 6 over x squared. You know, if y equals 6 over x, that's the same as 6x to the negative 1. Y prime, that is negative 6x to the negative 2. Downstairs, then I have kind of the same thing. It's just negative 1 over x squared. Then you could easily simplify here and here. You end up with the limit as x goes to infinity of just rather positive 6, right? Because it would be positive 6 left over. As soon as I get my eraser to work, there we go. 6 cosine of 6 over x. As x goes to infinity, 6 over x will go to 0. Cosine of 0 is 1. So 6 times 1 is our answer. Okay. Let's look at number, I think it's 11. I can't read my own writing. Limit as x goes to infinity of x to the 6 over x. So this form is infinity to the 0. And the way I like to do it, and you can do the way the book does, but I like to rewrite it as an exponential. So e to the ln of x to the 6 over x. And then pass the limit into the exponential and use the log rule, the power rule for logs to get 6 over x ln x. As x goes to infinity, 6 over x will go to 0. ln of x will go to infinity, so I need to rewrite that as a fraction. So I have e to the limit as x goes to infinity. It's pretty easy this time. It's just 6 ln x over x. Now you have infinity over infinity, so you can do L'Hopital's. E to the limit as x goes to infinity. In the numerator, I have 6 over x. In the denominator, I'll just have 1. Okay, so it will be 6 over x. As x goes to infinity, that will go to 0, and you'll just have 1 for your answer. Okay. The last kind is the infinity minus infinity, so I have the limit as x goes to 5 from the right of 50 all over x squared minus 25 minus x all over x minus 5. Okay, so I'm coming into 5 from the right, so I'm thinking like 5.1, 5.01, etc. Right? If you put that 5.1 into the denominator, you're going to have 50 all over something small, positive. Okay, so what's going to happen is that first term is going to be like L over 0, which in this case is going to go to positive infinity because of the direction of approach. Because you'll have like 50 over something like 5.1 squared minus 25, where 5.1 squared is going to be bigger than 25, so that's going to be a positive number. And all of these terms in the sequence will be positive numbers. So it's going to be positive infinity. The other guy, the same kind of reasoning, minus, so if you put 5.1 into there, you'll have 5.1 all over 5.1 minus 5. So you'll have basically 5.1 over 0.1. 0.1 is 1/10, so that will end up being 51, right? And for the same reasoning, the next guy will end up being 501. Because it's going to be 5.01 all over 5.01 minus 5. So that'll equal 5.01 over 0.01, which is 1 over 100. So you'll have 501. So it's going to go to positive infinity. The next one would be 5001, right? Okay, so in these cases, you find a common denominator and rewrite it as one fraction. So if you look at the denominator, what is this? It's x squared minus 25 is x minus 5 times x plus 5. So in the second term, I need to multiply top and bottom by x plus 5. Okay. So I have then the limit as x goes to 5 from the right of 50 minus x times x plus 5 all over x squared minus 25. Simplify that numerator. This will be 50 minus x squared minus 5x. Okay, so that would just be 50 minus x squared minus 5x over x squared minus 25. If you plug in 5, you're going to get 50 minus 25 minus 25, which is 0. In the denominator, you also get 0. And that's one of our L'Hopital forms. So taking the derivative of the numerator, I get negative 2x minus 5. The denominator is just 2x. And then you could do a straight substitution. So negative 10 minus 5, negative 15, all over 5 times 2 is 10. So negative 3/5, or negative 3/2, rather. Okay. Okay, so after we got through the limit section, then we could attack, and I'm not going to put the numerical stuff like Simpsons and trapezoid rule on the homework, or on the test. It's in the homework, so I assume you're doing it. 8.8, though, is the improper integrals, and of course, to do these, we have to turn them into limits. First 13, we have an infinite integral, and I'm not going to put something like this one on the test. I saw it in the homework, and I'm like, wow, that looks kind of weird. So I figured I'd do it on this review here. Anyways, this thing right here, if you didn't notice, it's going to be a partial fraction decomposition. So anyways, rewriting it first as a limit of an area going to infinity, we have this expression. And then that's a partial fraction. So x cubed all over x squared plus 5 squared. It's repeated irreducible, right? So you'd have ax plus b all over x squared plus 5 plus cx plus d all over x squared plus 5 squared. Okay. Multiplying both sides by x squared plus 5 squared, you get x cubed equals ax plus b times x squared plus 5 plus cx plus d times just 1. Foil that first part, so apparently I got ax cubed plus 5ax plus bx squared plus 5b plus cx plus d. I need to equate coefficients in order to get this job done. So not much going on the left side here. On the right, I have ax cubed plus bx squared plus 5a plus cx plus, I guess, 5b plus d. So a must equal 1, b must equal 0, 5a plus c must equal 0, 5b plus d must equal 0, just equating coefficients. So this third part, you could substitute in 1 for a, so that 5 plus c is 0, so c is negative 5. plugging in 0 for b here, d must just equal 0. Okay? So our decomposition then, our partial fraction decomposition, when all is said and done, we're getting the limit as b goes to infinity of the integral from 3 to b of a, so 1x plus 0 over x squared plus 5, and then minus 5x plus 0 all over x squared plus 5 squared dx. Okay, I'm going to split this into two integrals. I'm going to have to do u subs on both of them. So I'll have a limit of the integral of this first guy. Let's do a u sub on x squared plus 5. So du will be 2x dx, and then dx will equal du over 2x. So I get x over u times du over 2x minus, I can factor out 5 integral. Let's do a z sub on the x squared plus 5. So I get dz is 2x dx, and then dx is dz over 2x. Okay, so I have then x all over u squared times, z squared rather, x all over z squared times dz all over 2x. Okay, so I have the limit of, I can factor out 1/2 from this first integral, and that would just be the integral of du over u, which is an ln, right? So ln of the absolute value of x squared plus 5. Then minus 5 times the second integral, you can factor out 1/2, so 5/2 integral, I'm going to have to write this one out, z to the negative 2 dz, and then this would be the limit of 1/2 ln absolute value x squared plus 5 minus 5/2 times z to the negative 2 plus 1 is z to the negative 1, and then divided by negative 1. Okay, and then I have to back sub on it. So I get the limit of 1/2 ln absolute value of x squared plus 5 minus, or rather it will become plus, 5 all over 2 times x squared plus 5. It would be 5 over 2z, but back subbing, you get the x squared plus 5. I have to evaluate it and take its limit. Okay, so evaluating it from 3 to b, I have the limit as b goes to infinity of 1/2 ln of b squared plus 5 plus 5 all over 2 times b squared plus 5 minus 1/2 ln of 9 plus 5 is 14 minus 5 all over 2 times, again, 14. Okay. Most of this stuff will just be, well, this part will go to 0, right? Because it's going to be L over infinity, so that's 0. These other last two terms are just constant terms. The first term is a troublemaker. Okay, it's going to go to infinity as b goes to infinity because it's the ln of something going to infinity. And the natural log goes to infinity as x goes to infinity. Okay? So it's going to be infinity minus something, which is just going to be infinity. In other words, it's divergent. Okay? Please note, you need to show all your integral work, even if it equals infinity. You can't just write, like, look at the integral and write divergent. Okay, that's not going to work for me. You got to evaluate the integral. Okay, I promise not to put one so nasty on the test. Let's look at an infinite discontinuity problem, and we'll kind of leave it there. So number 17, I have the integral from 0 to 7 of 6 all over the square root of 7 minus x dx. Okay, so here the issue is this upper limit on the integral. If you plug in 7, you'll have, and for the integrand, you'd have division by 0, which is bad. So I need to rewrite this taking the limit as we approach 7. And if you think about the interval here from 0 to 7, I'm going to kind of tack down a b value and then push a b towards 7 from the negative direction. So the limit, and you have to show me the direction of approach, right? So it's b goes to 7 from the left. Okay, so it's the limit as b goes to 7 from the left of the integral from 0 to b, and let's rewrite this integral as 6 times 7 minus x to the negative 1/2 dx. Okay? So I'm going to u sub on 7 minus x, du will be negative dx. So dx will be negative du. So rewriting my integral now, I have some sort of limit of the integral of 6 times u to negative 1/2 times negative du. So this will be the limit of negative 6 integral of u to negative 1/2 du. Okay, so this would equal the limit of negative 6u to negative 1/2 plus 1 is negative 1/2 plus 2/2, which is positive 1/2, divided by 1/2 is the same as multiplying by the reciprocal of 1/2, which is 2. I got to remind myself to evaluate. I need the back sub, etc., etc. B is going to 7 from the left. Negative 12 times 7 minus x to the 1/2, evaluated from 0 to b. So this will be the limit as b goes to 7 from the left of negative 12 times b, 7 minus b, you have to put in for x. So 7 minus b to the 1/2 minus negative 12, so plus 12 times 7 minus 0 to the 1/2. Okay. So if you allow 7 to approach b from the left, that's good. You'll have positive numbers inside the square root here. It'll just approach 0. And so you get this thing equaling 0, and you're just left with 12 times 7 to the 1/2, whatever the heck that is. Okay, so that would pretty much do it. Integrals, integrals, integrals. Basically everything integral except for a couple of limits, right? And that would be the whole test. Other than that, I think you should be good. I'm just looking through my notes and make sure I got everything. Okay, I think you're good. And we'll call it quits there. Thank you for watching as usual. I'll see you next time.